the most important duty or expectation from a good expert and engineer is that they can convert such practical to some conceptual physical model and then convert it to mathematical formulations with clear boundary conditions. But the point is that I think we don't have that much engineers, good engineers and experts that are able to convert the real technological process and natural phenomena to this. I think this is the main challenge.
Today I get to talk with Aliyar Javadi, the Scientific Director of World Academies. Dr. Javadi holds professorships at the technical universities of Dresden and Berlin. He also holds a PhD in chemical engineering and has over 20 years of experience in multiphase flow phenomena. Thank you to World Academies for sponsoring this episode. I hope you enjoy our conversation, and please like, subscribe, and hit the bell. Welcome to the show, Aliyar. It's really good to have you.
Thank you, Kate. It is a nice opportunity to talk with you about CFD and related engineering and scientific technological aspects today.
Yes. Yeah. So speaking of scientific technology and CFD, how did you get exposed to this and started? Did you always want to go into science and engineering, or what was your first experience?
Actually, I was always very interested in physics. I would say my first lovely topic is physics. And then, of course, mathematics and chemistry. But beside that, of course, I have been also interested in history, geography, literature. I'm not just limited or restricted my interest to engineering and fundamental science. But what I did in high school and at university has been physics and mathematics profile and chemical engineering. I started my bachelor in chemical engineering and then master and PhD also in chemical engineering. During my bachelor, I did rather a kind of polymer science and food industry. And during my master, I did something related to reactor designs as the main major. And also my minor was biomedical engineering. And during my PhD, somehow I continued my interest in transport phenomena. What I became very much interested during my bachelor time with fluid dynamics. And then during my master, also I became more interested in fluid mechanics and heat transfer, mass transfer. And then I continued multiphase systems and multiphase simulation during my PhD time. Then in general, I would say my main expertise is transport phenomena. When we talk in integrated mode, all three subjects of fluid mechanics, heat and mass transfer, or let's say transport of momentum, energy, and mass. And I like it very much. I am every day excited to understand more, either in the nature or either in the laboratory, because I have been also simultaneously beside my CFD simulations or my theoretical work, I have been also many hours, 1,000 hours in laboratories. In particular, when I started my postdoctorate at Max Planck Institute for Colloids and Interface, when I found opportunity to be more deep about interfacial phenomena between two phases of gas, solid fluid, and how molecules or colloidal particles move via Brownian motion, diffusion, or by convection, reaching to the interface, and after coming to the interface, according to the thermodynamic issues, jump to other side. This is a very important issue to be discussed maybe later. And then in second phase, we have also again both diffusion and convection. This has been my main interest, and I would be happy to share some part with you and audience today.
Yeah, we're excited to hear more about this. But before Before we dive into more of the technical things, I want to focus on where you're at now. You've started World Academies and as a platform. So can you tell us about that decision? Why did you choose to start World Academies? And what do you see the future of technical education looking like?
Actually, the story of World Academy in some aspects come back to more than 10 years ago in my mind. If I want to say something more clear, more than 12, 15 years ago, when just Google was appeared and even LinkedIn was in the first step, when we received emails sometimes from LinkedIn, try to be linked to the people, this was a new story. And in that time, I thought that was the age that Google somehow, let's say around 2010, that still Yahoo search engine also was still on the top, and Google, of course, was on the top. And I thought, beside search engine, we need also search society. It means that not only we should be smart to use technology and automatic search engine based research works like Google, but also we need to have real people connected together and try to move the state of the art of technology and science in the world. Because I believe that the basis of human civilization has been communication, has been interaction. And although internet is a very good tool that increase the speed of our communication for science and technology, literature, social and cultural aspects, but sometimes internet somehow can separate us from each other to be in direct contact. Then I had a wish,
Mhm.
okay, how we can also develop search society, like not just internet, we call it interman or interhuman, because internet means to have a connection networks between different IPs and different internet devices, PCs, and data, big data, a source of data around. But it is good also to develop platforms that humans also are connected together. Then the philosophy behind World Academies in that is interman or interhuman, to be connected together and search society, not just search engine. This was the philosophy more than 10 years. And then 3 years ago, with a group of colleagues and experts at Technical University of Dresden in Germany, we established our startup, World Academies, and we launched about 2 years ago, February 22, about more than a years ago, the first version of the platform, and we are going on now with this startup. Our startup somehow, I can say, in one side is going like an online university, a new generation of university. Here also there is a philosophy, and the philosophy is that for the real world, with more than 8 billion population, we have more than 6 million schools, primary schools and high schools running, and more than 100,000 universities. Of course, with the branches even is more. But many numerous universities and schools for the real world with 8 billion population. And we have another world, which is, let's say, digital world or online world or social media, different terminology. That's more than 4 billion, nearly 5 billion people are in this medium. But we don't have really online, let's say, universities and of online schools there. Although the real schools, like for example, MIT or Dresden University or Berlin, different universities try to be connected to online world via LinkedIn pages, Instagram pages. This is another story. We believe, and I believe that we need also university which are created from the material or from scratch from the social media and from the online students and professors theirs, because this is now more than a virtual world. Becomes a kind of parallel world with our present world. And this is why, if you think that how the educational systems are developed, one can think to 1,000 years, more than 1,000 years experiences, that how the schools are established, for example, for the first time in Asia, in Middle East, has been more than 1,000 years ago. Some school-like system developed, and then in Europe is more than 300, 400 years ago, the primary schools and today's schools developed. And of course, we know that the origin of some good universities in Europe goes back to more than 500 years ago. It means that for 8 billion population, now if we have more than 6 million schools and we have more than 100,000 universities, this is something developed within some 100 years. Now we have another world with more than 5 billion or nearly 5 billion users online, but
Mhm.
we don't have enough efficient, interactive, live universities and schools here. But human is spending time and energy here, and we need more efficient educational systems online. This is why we established World Academies, that in one side is growing like an online university, and in other side is a kind of novel scientific network, but more collaborative than similar platforms.
Yeah, it's great insight. So as you look at what you're trying to do, right? One of the main focuses is live interaction
Mm,
in the
mm, mm.
courses. And I've participated in several, and you invited me to lecture in one. And it's really exciting to see the amount of people that you can get from all over the world talking about the same ideas live in a course. So, one of the things that you mentioned through this is your focus is on learning, relearning, and deep learning.
Exactly.
So, can you talk about that trifecta per se a little bit more,
Mm,
and what your goals are and the format too? Because I think live is a huge part of this. That it's the interaction you're after.
mm. Yes, this is true. There are several platforms and websites, institutions that they provide online education. For example,
Sure.
Udemy, Coursera, LinkedIn Learning. But most of the lectures and courses available there are generally pre-recorded. And if there are also live lectures for some cases on some of these platforms, depends on the topics, still these are not enough group learning, because the level of interaction and live lectures the, is different. It means that, for example, if you go to a conference, a seminar, webinar, lecture, which is live, and just professor, instructor, presenter is saying something, showing many slides, and there is not open discussions, this is the minimum level of live, that yeah, this is live, but it is somehow comparable with pre-recording.
Yeah.
This, I think the level of interaction and being live is important. For example, let's say I want to give a lecture on fluid dynamics about the concept of viscosity or starting driving continuity equation as part of Navier-Stokes equation. When I start to talk about material and energy balance, depends on the knowledge and backgrounds of students and participants in the class. My examples and the way of presentation become different, because this is a kind of bilateral process, that it is important who is listening to you, if you have been in good mood to describe something properly or not, because maybe I cannot also always provide descriptions 100% efficient and correct. Then after I say some sentence, I'm asking from the students, okay, what is your idea about this? Or what you understood from my words? And then this becomes a kind of real interaction to learn together. I believe that learning, teaching, education should be really live and interactive like this. Then in our lectures, as you have also experienced that, and more than 1,000 students who had courses on CFD, fluid dynamics, turbulence, heat and mass transfer with us, they know that it is important for us that how they understand the instructors and professors, and then the next step will be somehow to move together, to learn together. This is what we do. And what I know, what we did also a research work with the help of sociology department of Technical University of Dresden. We did a survey, research survey about the available platforms for online education via social media and via online universities. If we need more tools, or what are the barriers, what are the wishes to have more efficient platforms for that. And our survey shows that currently we are much far from having enough online platforms and online universities that provide really interactive live courses and lectures. This is something that we try to do on World Academies.
Yeah, that's fantastic. One of the things I was just thinking about as you were talking, though, is the benefit of that. For people that don't know, there's a lot of research that goes into how we learn, and the importance of it being live is they call it the feedback loop, right? Of when you learn something and then you apply it and you get feedback, it reinforces the learning. And so one of the downsides of on demand or other things is you have to get feedback in a different way. And so the live course is one of the most effective methods of teaching and learning because you have that reinforcement immediately and you're able to correct any misunderstanding and things like that. So that's excellent. Switching gears here a little bit, you've had a lot of research experience and teaching experience in, as you said, transport phenomena, right? And so I want to ask maybe an industrial question of what do you see are the biggest opportunities for simulation in the process industries, right? Most of the time, transport phenomena is not maybe our typical external arrow, right? You look at a lot of CFD, a lot of the industry is focused on whether that's whatever vehicle it is, right? Whether it's ships, other things, I guess ships is less, but cars, airplanes. But what do you feel are the opportunities in the process industry for simulation?
Actually, I think the most important challenge to apply CFD simulation for practical studies like optimizing industrial process or developing new technologies is to understand the problem deeply. It means that I call it, for example, I call it the art of engineering. What does mean art of engineering? For example, you look at a process in industry. It is important that if you have a unit operation for heat transfer or for mass transfer or for some biomedical devices, how you can convert this part of technology and operation to some engineering model. I think this is one of the most important challenges still, because generally students, they are used to provide them exact questions. For example, you say, oh, I have a system with this volume, with this boundary, and some flow is coming from here, some goes from there. If flow rate is here or temperature is that, what is the pressure here? Or please predict what? These kind of examples, which is the most important part of education system, both in university and somehow also at research institute and in academic centers around the world. These are a kind of pre-processed examples. The real examples at the end, we want to have engineers and experts that they look to the nature and see, okay, there is a lake here, there is some water evaporation, there is some air pollution, or there is some water pollution here, or here we need some more energy, or here we have problem with this part of nature. Or you go to an industry and you see they have interest or need of more, let's say, saving energy. And these are the practical conceptual problems. Still, these are not well-known engineering problems. These are conceptual problems. And I think the most important duty or expectation from a good expert and engineer is that they can convert such practical process, part of technology or nature or domestic applications, to convert it to some physical, conceptual physical model, and then convert it to mathematical formulations with clear boundary conditions and input record input data. And then is a question that how we can solve this problem, either analytically, theoretically, or CFD simulations. If we can do this process to bring real physics or real nature, real technology, practical industry to some conceptual physical model, and then mathematical model, and then formulations like Navier-Stokes equations or other required equations, then if we solve it mathematically, theoretically, or by CFD, we can understand the results, if these results are reliable or not, if are physical or not, because somehow then we should go back. We convert the nature and industry to physical model, mathematical model, formulations, and then we try to solve. And after we solve, then we draw graphs, we provide contours and images of CFD, and then we provide animations, and we expect that animation is similar with the real physics. But the point is that I think we don't have that much engineers, good engineers and experts that are able to convert the real technological process and natural phenomena to this. And as we have problem in the first step, to bring it back to understand the results is also still need a lot of work. I think this is the main challenge. If I want to say, we should understand the problem better. Then we know this, then it is not difficult to develop equations or develop new CFD methods. This is one aspect. But if you ask me, okay, finally we are doing this and that, and we are doing a lot with CFD simulations, but what are the most challenges? I would say the challenges are more when we go, for example, to multiphase processes, or when we go to biological processes. Then we have complex physics and complex composition, and different interdisciplinary area are more challenging, but are more needed.
Yeah. Yeah, I love the way you described that, because when you look at, there's a quote, I think this quote sums it up best. I think it's by Boris and Oran. It's computational methods for reactive flows. But they make this exact statement. They say the skills required to conceptualize a problem are typically different skills than the actual analytics of solving the problem and executing it, right? And you look at, it's similar in business, right? You look at, to give a business analogy here, in business schools, people recognize that they were trained a lot more on strategy and business strategy and not execution. But the number one problem in actually running a business isn't coming up with a good strategy. It's executing that strategy day in and day out with a team. And so analogously, in physics and engineering, the amount of training that we have in analytical computation is orders of magnitude higher than the amount of training you get in conceptualizing problems. And so I love that. That was just an excellent description. Thank you so much for that.
Thank you as well. The
I
point
really
is that,
hope.
Kate, if you know your problem, for example, let's say you see someone and he or she don't feel happy, okay? Sometimes you ask, okay, what is your problem? This person can describe exactly what is the problem. For example, I have problem with hand, or I have
Mm.
problem with knee, or I have problem with. Then you can go to the doctor. To which doctor you should go and ask for a solution. The
Mm-hmm.
point is that generally in engineering, we cannot properly understand and define problems. The point is that if we are able to define well or develop well the physical model and mathematical model, then even you can go to a mathematician and say, look, I have a differential equation with this boundary condition. And sometimes the mathematician, they don't have any idea what is the physics here, but they can provide you,
Yeah.
okay, look, you can do this and that and try to solve this. But again, this is you that how you can use this solution. Again, when you go
Yeah.
to a medical doctor and they provide you some solution, this is you that you have to apply the recipe of the medical doctors. It means that
Yeah.
we should understand the problems. Otherwise, we cannot use CFD simulations in proper way. And there is no also enough motivation when you don't know the problem. There is not enough motivation to follow these long formulations, discretizations, and CFD process. But when you know exactly the problem, these are not really.
Yeah. Yeah. That's excellent. So, follow-up question then, how do you try to incorporate conceptualizing models in your courses, right? We've identified it's a skill that's not focused on as much. So how do you try to focus on it in your courses that you offer through World Academies?
Okay, for me, my teaching style, which is related to my learning style when I was at high school. When I was at high school, I had a look behind what was learned. I learned in middle school and in primary school. And when I was in a bachelor duration, still I had a look to my books in high school. No, never, I think, what I learned in high school has been completely 100% perfectly delivered to me. I think learning science should be similar to the literature and communication. I make you an example. I think we had also once this discussion. You know that every language has several thousand words and terminology. For example, English, I think the essential words and text that we need to be able to do communication in English is more than 10,000 words, 20,000 words. Most of the languages have some 10,000 words. And children learn these words within 5 to 7 years, maximum 10 years. They know a lot for communication, even after 3, 4 years. But when you think about the fluid dynamics, maybe the fluid dynamics, you can say we have 50 or 100 important terms and parameters that if we know them deeply and clearly, it is not difficult to understand different problems and situation and do modeling and simulation. For example, what is density? Still, if you ask many educated people that at least they finished high school and they had for sure a part of physics or chemistry or biology or general natural science, they had something about density, but they cannot properly define it. They cannot apply and use it. But density is comparable, for example, with the price of different things that when we go to shopping, and for example, when you buy 3 kilogram apple and every kilogram, for example, is €1 or 50 cents, whatever, then you see that even non-educated people and children with 7, 8 years old, they can go shopping and do shopping and they buy many things and they calculate everything and they know exactly what is going on during shopping process. But when you go to the matter of density, that you say, okay, density is the mass of unit of volume. Many people become confusing of this description. And for the price also is this: if we don't have experience of shopping and just explain, okay, what does mean price? Price is the value of money with certain currency that you pay for the unit of mass or unit of volume of something. Maybe you define this 5 times or 10 times, but if we don't do shopping and if we don't go to shopping with our parents, again, we forgot what is price exactly and should be calculated, considered according to the unit of mass or according to the unit of volume or according to the number. And this is the situation, for example, in thermodynamics. For example, if I ask you how we calculate internal energy, many engineers and experts, even they cannot reply quickly to this question. And the other people in other area, either they cannot. But when we talk about the internal energy, we already define also heat capacity, that we say this is a heat capacity. The heat capacity is the amount of energy that you need to provide for the unit of mass of a material, for example, 1 kilogram of copper or water, to increase 1 degree of temperature. This is comparable with what we understand and we do during shopping when we have, for example, 2 kilogram apple, how we calculate the amount of money that we need or paid or received. The internal energy also is calculated in this way. We define some heat capacity for the unit of mass, and then we calculate that. Or, I mean, everything, when you look into different part of Navier-Stokes equation or how we calculate the right continuity equation, all are related to such a very basic definition. But the point is that generally in education, we want quickly define viscosity, density, pressure, and then we want to run many questions in practical situation and expect that the students can understand and develop the models and analyze the solution that we want. But what I want to say is that how we learn literature and communication language, for example, to be brave or to afraid of something, or what does mean freedom, or what does mean hot or cold, or time, late or early. These are very complex words. Just think about the concept of some of these words that at different age, at different situation, the concept of these words can be interpreted in different means. These are not easy, but how we learn this and you have common sense and understanding about that, because 100 times, sometimes 1,000 times in different situations at home, at kindergarten, at primary schools, by parents, by teachers, by friends, we are in the situation that they describe us the concept of each word that we need for communication in life. But this is not the situation at university. Maybe once you go to some fluid dynamic course and the professor write, okay, what does mean viscosity within 2 minutes, and then they start solving problem. I think viscosity or density or acceleration or velocity or heat capacity, diffusion, whatever word and units and terminology that we use in engineering, this should be taught 100 times from different situations, and not only in the first course of fluid dynamics during my bachelor time, maybe in master, in PhD, again and again, we should update our understanding and the way of description. For example, if I ask you, what does mean freedom? For 3 years, child, freedom has a meaning, but when you are 10 years old, this meaning is updated and is more complete. And then you are a teenager, and then you are in 30 years old. And still, when you come to 40 years, 50 years old, you say, oh, now I understand another meaning of freedom that you didn't know within 50 years. The concepts in science also should be in this way. We should not hesitate that still I don't know what does mean viscosity in the way which can reply and can be applied to many questions in different situations, 2D, 3D, different geometry, non-Newtonian situation, term, non-isotherm situation. The point is that somehow we try to briefly and shortly define key concepts and then apply it. As you said, we are trying rather to apply science, not to learn science. To learn and educate science, we should have patience and step by step talk about it. Application of science should happen later by the experts and engineering. They can apply it to numerous different questions and situations. But the point is that we make short education of key concepts, and then we have to teach them 1,000 different situations. It means that let's think that I don't know what does mean exactly society. I don't know what does mean exactly freedom. I don't know exactly what does mean hot or cold or early, be kind or jealous. If a child don't know this, when he or she goes out to the kindergarten and to the street, always would have problem to understand the situation. And maybe the parents should go and say, look, here jealous means this, here's freedom means this. It means that if a child is not well educated with the basic words, always have problem to be in communication with the friends and practical situation in the society, in the school, in the workplace. And this is what we do for the science. We make short education, and then we have problem for thousands or millions application, because we have millions application and different situation, different material, different condition, different geometry, different time and space resolution. And always we think, oh, this is a new problem. No, this is not really a new problem. This is somehow a known problem, but if we know the basis exactly.
Yeah. Such an excellent description. And I just want to give one anecdote of my own personal life. So I was working as a CFD engineer, and I made a simplification, a conceptual model, and I applied it. And later on, I was interviewing for a different job, and I was asked fundamentally the same question that I have made a conceptual model of, but I wasn't good enough in my breadth and depth to say, oh, I could do the same thing for this problem as I could for this. And so during the interview, I stumbled through it, and it wasn't clear to me. But then after lunch, this was a full day interview. After lunch, I was able to talk with the hiring manager, and I was like, yeah, I just connected the dots. I did that exact same thing in a different setting here. And he was like, yeah, that's exactly what it would be. That conceptual model would work. And so I just love how repetition is natural and normal for learning. And I think we don't, for some reason, that's lost on people, and they feel like they're broken or something's wrong if they have to repeat concepts in science and engineering. And then number two is I've personally seen that in your course, the ones that I've attended, that for anyone listening, what I can guarantee you're going to get out of World Academies and a course from Dr. Javadi here is if it's not evident to you that he loves this subject, then yeah, you can tell. But two is the time spent talking and interacting to get to the bottom of that. And in my experience, professors are very busy, but there's a different feel in Dr. Javadi's classes. And so I can guarantee you're going to get the depth and the time. And I actually just want to pull. This is my most recent textbook I've purchased because of you. You posted about it so often.
With the bottom
yeah. Yeah, it is. Yep, the bird. Yeah, I saw it in the background. That's why I thought, oh, I need to pull this up. What it reminded me of as you were talking is I love how different textbooks talk about things in a different way, and they repeat them differently, and I get an extra layer of understanding. And not that I have time to read through the entire textbook, but as I look up a subject or look up a topic, it reinforces it and expands my understanding and my depth and the clarity. So, Dr. Javadi, what are major opportunities that you're seeing for new professionals entering the field of scientific simulation, specifically CFD? But it's really still early, as you talk about in the process industries, right? Multi-phase. There's still a lot of work to be done. So, what do you see are the major opportunities
Yes.
for
The
people
point is that,
picking this as a
Kenny,
career?
this is true that still for multi-phase simulation, uh, we have some models, very good models, that we can predict, for example, how the interface of two phases are moving and how we can track them. We can predict many situations which are needed. But the point is that still there are many challenges open, and somehow the projects in multi-phase flow simulation in one side can be called or considered industrial, practical projects, and in other side are research projects because are very close to the state of the art of developing science in their related fields. But the point is that not only we have challenges for understanding multi-phase flow computationally by CFD simulations or other um, approaches and computational methods, but also we have problem also to do experimental analysis for multi-phase processes. Do you understand me?
Yeah.
Okay, because I thought maybe it is disconnected. It means that sometimes people say, look, still multi-phase flow simulation needs to be developed with better accuracy and lower computational costs, more reliable and reasonable results. Yeah, this is true. We have to do a lot for that, and there are a lot of open questions. But in same time, we have also challenges and problems for experimental characterization. It means that still, when you want, for example, you spray 1 liter liquids like water, and you want to predict the droplet size distribution of spraying 1 liter water. This is not an easy question. It means that if you want to do this experimentally, not 100% you can do the reproducible experiments. It means that if by an injector spraying technology, you spray 1 liter of water today, and then you try to characterize and record it, you need high-speed camera, you need 1,000 gigabytes memory to record formation of all small and bigger droplet and how the breakup of droplet, jet breakup happen, if there are any coalescence of droplets or not, and how is size distribution and interface merging or breakup, and how is the speed of different droplets in different positions. You need a large memory and very relatively high technology, a fast camera for this, and this is time consuming. And if you have a little bit of salt in the water, if you have a little bit of detergent, surfactant, proteins, impurities in this liquid in water, for example, then the size distribution and everything can be changed. That how can be sensitive. And if you repeat the experiment, it is difficult to say 100% if you can have 100% reproducible data. Now the point is that, okay, if you have such a big challenges to characterize this system experimentally, what about CFD? Although we have also problems in CFD, but any results that we can provide by CFD simulation is a very important, because we have already problem to understand the system experimentally. Although we have limitations in multi-phase flow simulations, but as the experimental characterization also is expensive, time consuming, and for most of the cases, not 100% reproducible, we have to develop simulation methodologies, both according to the physics, that how we interpret the physics of interface, the physics of coalescence or breakup, and then the computational approaches to track interface and simulate the project and analyze the results. Then we should develop this in parallel with experimental methodology. This is the real need. Then any results for simulation of multi-phase processes are very valuable.
Yeah, it's the as you pointed out, one of the biggest troubles with multi-phase is collecting validation data.
Sure.
But not even validation data, but data upon which you can analyze to help you form
Yes.
an analytic or a computational model, right? To understand the system. So it's a multi-layered thing. So I just want to emphasize, I bring this up because at one point in my career, I had one of my mentors, he was talking about fluid mechanics, and he basically made a comment like, oh, all the cool research has already been done. And it was a really disheartening thing. So I just want to emphasize to everyone, if you're ever feeling like there's not great opportunities, there are plenty of opportunities for fluid mechanics research and better understanding things. Thank you for
And
that.
not only
for that
this,
explanation.
Kate, I should note that multi-phase process is everywhere. This is not just a small part of technology or nature. We can say in our body and nature and many industrial processes, we face with multi-phase simulations. We cannot just, or let's say, rely on our methodologies and results on single phase, because generally we face with multi-phase situation.
Yeah. There's a book I'm reading right now. I just finished it actually, but it's 5 Equations That Changed the World. And it talks about Faraday, Bernoulli, Newton, Einstein, a few others. But one of the things that stuck out to me that's relevant to our conversation here is that oftentimes today, one of the things I think I see people do is they compartmentalize themselves. They say, oh, I'm in this part. But a lot of these early scientists and the ones that really figured things out, they had a deep understanding that enabled them to go broad. Now, they weren't experts at everything, right? But they could handle different domains. And it was like you said, right? If you look at it from just the application instead of the science, you will limit yourself. But if you get a deep understanding of the science, you can do tons of applications.
Exactly. This is a very important point, Kate. Again, coming back to discussion point that we had some minutes ago, you know that how many numbers we have? We have just, let's say, 10 numbers from 0 to 9. Then we build billions number out of that, from this basic
Excellent
number.
analogy. Yeah.
The point is that if you ask me or some experienced people in different fields of science and technology, that how many types and system of multi-phase flow we have, one can say billions. Because although we have just 3 phases of gas, liquid, and solid, and maybe also plasma, but the point is that you have different liquids, and then different liquids when it comes to different gas or solid, and then you have many dissolved material, solid material in that different concentrations, different pressure, different temperature,
Different property
different
fluids.
viscosity. When you think about it, we have billion case studies. And sometimes you see that engineers and experts are trained that you have to always have some validated experimental results and do some simulation to compare this together. No. We should be able and trained in powerful education systems and deep understanding that when we don't have also experimental results, if we face in some situation, we can rely on our simulation and modeling results according to the deep understanding of key concepts that we have. For example, I say a book like Transport Phenomena of Byron-Baird or Fluid Mechanics of White or Sengen, maybe these are 1,000 pages book, but 10% of these 1,000 pages book are very important to be educated and discussed. And even
Mhm.
if even in these 10% of pages, 10% of these 10%, there are key concepts that should be discussed deeply and repeated several times to be understood completely. It means that generally there is 1% important key concepts and terminology and basic concepts in 1,000 pages reference books that we have to understand it well, and we have to talk and discuss about it several hours. And after that, 99% will be explored. This is something that we need in education, I think.
Yeah. Yeah. Excellent. Excellent observations and excellent discussion. Thank you. Thank you so much, Dr. Javadi. This has been fantastic. So
Thank you
really
as well.
appreciate it.
It was a very nice discussion for me. Maybe we can continue with other aspects, but just maybe today or tomorrow, I will release also a post on LinkedIn that I
Yeah.
summarized and did a recap of 10 posts. Then I described Navier-Stokes in simple words, or how
Hmm.
we Navier-Stokes from very basic equations of second Newton law, F equal to m product A, because this is something
Yeah.
that still everybody can understand from the basic physics of high school. How we can
Yeah.
start from very small basic concepts to develop big equations, Navier-Stokes
Hmm.
in simple words, or how we can understand continuity equation not only in mathematical formulation but also conceptually. It means that all equations in fluid dynamics, heat and mass transfer, and in engineering generally, they have some physical sense and concept behind. We should, in
Hmm.
parallel, or learn both. Otherwise, this will be just, yeah, tons of equations and bulky equations and not attractive. But when you know the concept behind, you can drive them easily, and would be easy to take in mind also.
Yeah.
Thank you.
Yeah. Yeah. Looking forward to it. Thank you again. Thank you for listening. Really, thank you. Did something about this episode stand out to you? If so, please go ahead and share it with others on LinkedIn or other social media so they can find this as well. See you next time.